Hi, I'm Patrick from 7-Bit Wonders, and today we're starting a new series where I solve USACO problems and hoping to give you a useful insight into how to solve them and give you the mental framework to solve them efficiently too. Today, we're not starting with a bronze question or a silver question, but a gold question which I hold dear in my heart, which is the 2020 February contest, Help Yourself. I believe it's one of those problems which at first looks impossible to solve using the bounds they give, but once you understand the trick, it just clicks. So, without any further ado, let's read the problem statement. Bessie has been given n segments, which go from 1 up to 100,000 on a one-dimensional number line. The ith segment contains all reals such that this inequality holds true. The union of a set could be interpreted like the one you know from grade school, right? Such that if there is a common point or a common area between the two intervals, they are one. They merge and they become a whole together. What they've worded it here is a bit complicated, but it means kind of the same thing. The complexity of a set of segments is the number of connected regions represented in its union. Or, in other words, disjoint intervals. We will see in the drawing what this means exactly. Bessie wants to compute the sum of the complexities over all 2 to the power of n subsets of all the given n segments, of course modulo 10 to the power of 9 plus 7. Unfortunately, we are Bessie and we need to help ourselves, which kind of sucks. So, the first thing we could do is look at the explanation, right? We are given this input and this sample output. In the explanation, right, every single possible subset is given and basically doesn't tell us as much. Why? Because in most of them, the interval 1 and 6 eats up all the others, right? So in a reunion, it's the only significant segment and the complexity is 1. The only significant subset would be this one, where we can clearly see there is a gap between 3 and 4. We will see in the drawing how this looks exactly, and I believe it will click. Of course, in the way it's worded, it looks like a backtracking problem, but because the constraints are so tight and this is a gold problem, backtracking won't fly. So, what's there to do? Basically, the trick to this problem is understanding how a segment contributes to a component. And to better understand that, I believe it's much better to visualize it. But before we do, we need to look at one important line which will help us in solving the problem. Basically, we see that these ranges are distinct integers, and in this range, which would guarantee that our approach will be correct. Right now, this may look random, but will play a very, very important role later down the line. So, here is the example input visualized on the one-dimensional line. As we can see, all the subsets which have 1 and 6 will be of complexity 1 because 1 and 6 is basically the entire line. The only exception being if the segment is by itself or if we look at these two disjoint intervals, which are clearly disjoint because there is a missing link between 3 and 4. So what's there to do? Maybe we should look at how a single segment acts as a starting point for a component. So let us consider a segment which starts at L and goes to whatever. It's not important. We only are interested in the starting point. If there is no bridge of the form L minus 1 L, we may affirm that there are no bridges which would eat up this segment, and that means that the segment which starts at L is standalone. Now, of course, these bridges may start at L minus 2 or L minus 3, but in the way we will code this logic, it makes sense to only look at the space one step behind. Just you have to stick around and you kind of understand why. But it's important that we keep this consistent, right? With everything out of the way. Now, we could say that there are exactly 2 to the power of n minus 1 minus c possible segments or subsets of segments where this component, L and whatever, is the starting point. But now let's break down this formula. We know from grade school that in a set of n elements, there are exactly 2 to the power of n subsets. So we can write it down. We subtract 1, which means we subtract the segment we want to act as the starting point. Basically, we fix it in place and we only look at the others to fill the gaps and create a valid subset. Now, what's interesting is this C. And this C is basically the amount of bridges which would render this starting point useless because it would be eaten up by something which comes way before it. So we subtract it. With this little formula, we have found all the possible subsets which use this particular segment as the starting point. And if we extend this logic to all of the segments, we may say that the answer we have been looking for, or basically the complexity between all n sets, would be the sum from I equals to 1 to n of 2 to the power of n minus 1 minus ci, where ci is basically a generalization and means all the bridges which come before component I. And basically this is 99% of the problem done. We have found a formula which helps us calculate the complexity in O of n time complexity. But now the next question is, how do we calculate the number of bridges? To do this, we need to go back at the sample input and we should simulate how we would do this. Basically, we have 3, 1, 6, 2, 3, and 4, 5. Now, let's create a little table from 1 to 6 where we would add 1 for each point that is visited, right? So, for instance, when we read 1, 6, we add 1 through every index because we can walk to it exactly once, right? From 1 to 6. When we read 2, 3, we add 1 to 2 and 3, and 4 and 5 is the same. So, at the end of the reading operation, we have this table. And if, for instance, we were curious about the number of bridges which would connect 2 to 3, we would simply have to look here. And we would see there are exactly 2 bridges because this place can be reached 2 times from here and here. Now, if we were to simply implement it like this problem would have a O of n squared time complexity because of how updating this range would be. In the worst case scenario, we would have to do this a lot of times, right? And manually adding 1 to each component would add up to this time complexity, which is bad. However, for all of you seasoned veterans, you would already know a strategy to circumvent this and get the optimal O of n time complexity. And that would be to use the difference arrays, which would mean instead of, you know, uh, filling the table every time we read something, we simply look at the interval heads, right? We modify it in constant time, and only after we finish the reading operation, we create the difference array, and we would reach this table in a simple linear sweep. This is how we optimize the problem and get O of n. Now, I will not explain what a difference array is here. If you want to, I can make a video on that, but there are many great resources online. But basically, this is the missing puzzle piece to solve the problem efficiently and correctly. Now, with this out of the way, we have finally laid everything on the table, and we may finally go and code the problem from scratch. Now we may finally go to implementing the problem. Let's change the problem name to help, because that's how the input and output files are named. The upper bound for n, and the mod. As we've seen, we have to calculate large powers of 2, which in the easiest way possible, we could pre-calculate in an array, which we will use when we have to calculate the sum over all the possible subsets. So let's do that here. Let's create a prec, which pre-calculates all the powers of 2 up to 100,000. See? Let's create a function called pre-calculate, which does the exact thing. The first power is 1. And for I equals to 1 to 100,000, I plus plus, prec of I is 2LL times prec I minus 1 modulo mod. Do keep in mind I use 2LL because there is a possibility where we go out of bounds and we don't want to have an integer overflow. So we cast it to a long, and then after the modulo operation, we ensure it's an int. And this is the precalculation part done. Let's also create a struct called segment where we will keep the segment heads. This will be important for the last part. And R, right? And let's create an array of segments of size n max plus 1 because we have indexed from 1. Now the last thing we have to do is declare our n, the difference array, which should be of size 2 n max plus 2. Next is the prefix, which would basically be the final array after we apply the difference array technique, which is of the same size but plus 1. And that should be all. Let's calculate the powers of 2. We read n for I from 1 to n. We will read the segment heads. So Cin segments of I dot L and segments of I dot R. And this is a little observation which we should make in the classic difference arrays technique. We would have to increment the L position and decrement the position at R plus 1. But in this case, the first part holds true. So we would increment the part at L, but we would have to decrement only R because in this context, the difference array doesn't account a point, but a bridge from I to I plus 1. And if we were to decrement R plus 1, that would mean there should be a bridge from R to R plus 1, which, if you remember the drawing, you could go back, doesn't exist. So because of this different way to look at the array, we need to go one position backwards. Doing this ensures we have a correct code and no offsets errors. Good. With this out of the way, we may finally create the prefix. So from I equals to 1 to 2n, we may create the prefix. Oh, good. That's very good. Prefix of I is the prefix of I minus 1 plus the difference array at I. And we finally created the table we have seen in the drawing. And now we may finally calculate our answer for all the possible subsets. So for I from 1 to n, I plus plus, we will create two variables. Good. And C, which is the prefix of L minus 1. Good. And now the answer is simply answer plus the pre-calculated power of 2 of n minus 1 minus c. Of course, everything is under modulo. And this is basically it. We have finally solved the problem correctly. Let's save our code. And let's use a command to see if everything works correctly. We have passed the initial test. Now, let's submit the problem. And as we can see, we only have all greens. So this was the problem. I hope you understood the thought process behind it. As you can see, it's a very, very interesting problem. Definitely on the harder side, perhaps, when visualizing because of its neat linearity by contribution, which is basically what we've proven with the drawing, that you only have to look at all these segments and basically remove the bridges, and you can basically compute all the subsets in linear time, right? The sum of complexities of all the subsets in linear time. I believe this is one of the best problems of gold in combinatorics. and one of my favorites. If you've enjoyed the video, don't forget to leave a like and subscribe. If you have any suggestions, please leave them in the comment section below, and I'll definitely see you in the next one. Bye!